Okay, hello everyone. I wanted to do a video about the second problem on the recitation. The reason being that when I took this class, I found this problem really difficult to learn within the recitation, and I would have loved a video explaining the solution. So some prerequisite knowledge. The main thing to remember from the lecture for this problem is that for any algorithm that can find the max number on a set of n inputs, that algorithm has to take at least n minus one ops. And remember, we're in the comparison model. So the only operation is comparing two elements. And another thing to remember is this idea of having like these binary trees represent certain algorithms. Because we only have comparisons as operations, you can view an algorithm as just a big kind of chain of comparisons, and you can model that by having a binary tree. If one comparison yields one result, you go maybe down the left branch. If it yields another result, you go along the right. And so for this specific algorithm, let's say we have this algorithm called T that solves the max number. We have this kind of barrier cutoff of at least n minus one ops, where any leaf has to be below this barrier. And in this situation, a leaf is kind of this, like the algorithm stops, it found the solution. Another important thing to remember is that just because a leaf has to be below this, it could be much further below. You could have maybe the algorithm takes very long, much longer than just n minus one ops in some scenarios. So now let's move to the recitation problem, which is talking about algorithms that find the top two elements. And we want to do some sort of lower bound for that. And here's what we're going to do. Let's say that we're given some sort of algorithm, let's call this A, that solves this top two. We call this top two problem on n inputs. So here's what we're going to do. We are going to look at this algorithm A. We're going to look at A, and we're going to create an algorithm B. And where B solves just the max problem, where this solves the max problem. And by doing that, we can use our analysis that we did in lecture on the max problem on B. So how do we do that? So this is when we start bringing out these binary trees for algorithms. So for A has some binary tree. So it's like it has some algorithm that it uses to solve okay. So A has some binary tree algorithm that it uses to solve the top two inputs. And for each one of these, remember, these leaves output some sort of index, or two different index, I and j, for the top two. And here's how we're going to use A to solve B. So or to solve the max problem. So how we're going to do it, we're going to solve B. So I'll just write some pseudocode. So let's say we're given a list of n minus one, of size n minus one, and we want to find the max. Well, what we're going to do is we're going to append infinity, or just a really large number to the front. I don't know if that's append to front, or you can think about it as we're going to put it at index 1. So what it looks like is that when we're doing this, is that maybe we're given like a list or like 1, 3, 7. And we're going to make it into a list of infinity, 1, 3, 7. And once we have that, now we're going to run A. So now this is when we're going to run our algorithm A on this list. Okay. Why are we doing this? Well, when we run this algorithm A on this list, we know a couple things. We know that the maximum element is in the first index. So when we look back at our binary tree, if we look at all the leaves that the max index was 1, so maybe 1, then like 1, and 1. Our new algorithm B is going to contain all of these paths to one of these possible outputs where 1 is the max. So we can think of this new, if these three leaves are the ones that 1 has, we can think about it is that B's binary tree looks like this. So it looks like bam, bam, 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this is what the B binary tree looks like, because we went over and we just have all of these nodes. Because this is what the algorithm looks like. The algorithm will never go to any of these other branches because we know that the max index is at the first index. So this is our B binary tree. We have a bit of an issue though, which is that there's a lot of junk in this algorithm. So for example, let's look at this node right here. It has to go to the left. So in a sense, if you were to see in Python code, we have a situation where we'd have like if 0 is less than 1, do some code. And then otherwise, like else, I don't know. I'll say like this is code alpha, and like this is code beta. But 0 is less than 1. So this code would be the same as just code alpha, running code alpha. And it's similar over here. We're doing an operation that we don't need to do. And so simply running this code on this new list gets us this binary tree. But now I'm going to claim that there's another program C. Let's use green. So there's another program C, which is kind of the optimized view. In which it only does the operations that matter in a sense. So in here, the only operations that matter are the ones in which there are potentially different results. There are potentially leaves. And so this one, so now it's like this, and this. So now this code C's binary tree has the leaves and then also the kind of important nodes. So bam, bam, bam. And now something to note, both programs B and program C are valid algorithms to solve the max number problem. So for both of these, there is this restriction. There's a restriction that it has to take at least n-1 or n-2 ops. Because remember, at the start, we have a list of n-1 elements. And because of the thing from lecture, we know that any valid program needs to take at least n-2 operations, which means that both B and C require that any possible path to a length to any individual leaf must have at least length n-2. One more thing I want to note before I'm going to erase this in a second. The number of leaves in C equals the number of leaves in A. So I'm going to say like number of leaves in C equals the number of leaves in A. Number of leaves in A. Or in B. But these, the number, like all these leaves that were in B correspond to leaves that were in A in our original algorithm that where the results had the index I being returned as index 1. So I'll erase this. So now this equals the number of leaves in A of form 1, some. Okay. This is all stuff we need to know. Okay. Okay. But now let's think about C, because remember, C is our optimized version. And what we meant by optimized is that in C, it is a full, I'm going to say full binary tree. What I mean by that is that every node either is a leaf or it has 2 children. Otherwise, it wouldn't be optimized. We could have deleted that node. So every leaf, every node is a leaf or has 2 children. Node is a leaf or has 2 children. Now this gives us the ability to count the number of nodes. Because since it's a full, or count the number of leaves, since it's a full tree, since every leaf has to have at least n-2, a path of n-2 to get to it, this means that the number of leaves has to be greater than or equal to 2 to the n-2. And that's how we get it. So now coming back up here, the number of leaves in C has to be greater than or equal to 2 to the n-2, which is how, using this equality, we get that the number of leaves in A of this form has to be at least greater than or equal to 2 to the n-2. Okay. From here, that's, I believe, part A. Part B is to say, well, this is just if we decided to put our infinity, like add our infinity at the first index. So now we note that when we go all the way back to when we made our algorithm A, we could have put infinity at any index. Which means the number of leaves in A of form 1, blank is greater than or equal to 2 to the n-2. And using the same logic, the number of leaves in A of form 2 blank is also greater than or equal to 2 to the n minus 2. And the number of leaves in A of form 3 blank has to be greater than or equal to 2 to the n minus 2. And so when you go all the way down, for every single index, you have that, you have this inequality, which means that the total number of leaves in A has to be greater than or equal to n times 2 to the n minus 2. And now this is how we can now get a lower bound by just taking the log. So the min path, you take the log of n 2 to the n minus 2, and then you get, what is it? N plus, sorry, log base 2 of n plus n minus 2. And now you have your lower bound. Let me make sure I just didn't miss anything before I Yeah, seems good. Alrighty. I hope this was useful. Thank you.